Large language models can process millions of pages of military doctrine and output perfectly structured operational plans in seconds. When a commander asks an AI to draft a logistical plan for reallocating supplies, the model immediately drafts a clean schedule. The output is grammatically flawless and logically sound. But in a high-stakes environment, linguistic coherence is different from operational truth. The model might recommend deploying a specific heavy transport vehicle that the authoritative maintenance system flagged as disabled 2 hours ago. Generalized reasoning engines predict the most probable sequence of words. They have no inherent mechanism to check the current physical constraints of the organization they are assisting. Relying on fluent language generation to drive command decisions introduces severe operational risk. Producing a linguistically plausible sentence does not mean the system understands the institution's operational reality. This gap exists because models operate on semantic knowledge. They understand standard operating procedures, historical patterns, and how concepts generally relate to each other. An AI knows exactly what an emergency operations center is and what personnel it typically requires to function. Operational reality, however, depends on the specific, time-bound facts governing the institution right now. It must identify which specific emergency center holds lead authority during a crisis at this exact minute, and who has the clearance to access it. A common assumption is that simply pouring millions of internal documents into a data lake bridges this divide. But searching an unstructured data lake surfaces every conflicting memo and outdated schedule, leaving the model to navigate an archive of contradictions. This challenge requires a methodology for mapping how an organization actually moves, how it authorizes actions and validates states. This framework, the energetic paradigm, treats institutional intelligence as a flow of capacity. Integrating AI into operations requires a structured interface that connects machine reasoning to the institution's physical and legal reality. Start with a highly capable language model, isolated from the environment it assists. To anchor this model, we bind it to stable objects. The system maps fixed organizational entities, vehicles, personnel, facilities. A single aircraft might appear in maintenance logs, scheduling software, and fueling databases under different names. The AI needs a singular, resolved identity for that object. But reality is temporal. We introduce state. These entities exist under conditions shifting minute to minute. That resolved aircraft might be flagged as available by scheduling, but disputed by logistics because of a pending parts inspection. If the AI encounters this conflict and silently averages the data to give the commander a simple yes or no answer, it commits an error known as false state coherence. Forcing a clean, single response out of contradictory data destroys operational honesty. A safe architecture must recognize when facts are actively disputed, preserve that conflict, and explicitly expose it to the human operator. Understanding the environment is only the first step. The risk profile changes entirely when the AI attempts to interact with that environment. Creating a valid plan does not automatically grant the jurisdiction to execute it. This introduces the authority boundary. Institutional power requires explicit permission. Technical access is not the operational right to use it. Delegation must come from a human actor, and that delegation has to be narrow, mission-specific, and strictly time-limited. Machine reasoning must remain strictly gated by explicit human jurisdiction. Without those gates, automated execution functions as organizational sabotage. Even with strict boundaries, high-stakes environments generate unpredictable variables, and logic models will occasionally hallucinate or fail. This brings us to traceability. Every automated decision must have a mapped, auditable causal chain. Standard server logs and massive event dumps fail to provide this. They offer a chronological list of options, but they do not explain the reasoning behind them. Investigators need a clear chain showing which dataset was consulted and which authority approved it. When downstream reality contradicts the expected outcome, the system triggers a correction loop, halting further action and reverting the object state. If an automated process executes an error that the institution cannot reverse, the system has failed at the most critical level. Placing a human in the loop without giving them the immediate technical power to suspend or reverse a machine action is merely ceremonial oversight. The safety of an AI deployment is measured by the organization's capacity to quickly detect, contain, and recover from its mistakes. Zooming out, we see the energetic paradigm as a complete, unified operational layer. Institutional intelligence is an emergent property of this entire arrangement. It does not exist within the language model alone. Hardware advances rapidly, and base AI models are constantly being updated or replaced. The true source of long-term operational power lies in this stable architecture. It protects the institution from the chaos of constant model churn. Procuring a faster or more sophisticated base model does not automatically purchase institutional competence. There is no autonomous, plug-and-play technical fix for complex government and enterprise operations. The ultimate responsibility for establishing authority, maintaining governance, and setting the strategic goals remains stubbornly human. An organization cannot safely automate what it has not structurally modeled and institutionally bound.